Stop writing loops. Stop coding gradients by hand. It's time to build a brain. This is PyTorch, and we are going 0 to hero right now. Welcome to the PyTorch Masterclass. Forget the boring lectures. We're going 0 to hero in 12 minutes. Chapter 1, the tensor. It's just a list on steroids. Step 1, import torch. Standard stuff. What is PyTorch? It's a library created by Facebook for building neural networks. It handles all the complex math for you. Millions of engineers use it daily. It's free, open source, and powers Instagram's filters, Tesla's autopilot research, and most AI startups. You don't always manually type numbers. Usually you want a blank canvas. Torch.zeros gives you a grid of nothing. Torch.ones gives you a grid of, well, ones. Why would you want a grid of zeros? Because neural networks need a starting point. Before training, weights often start as zeros or random values. This is how you create that blank slate. Torch RAN, the N stands for normal distribution. This creates random numbers following a bell curve. Most values near zero, few values far from zero. This is how we initialize the brain of a neural network. Random starting points, then we train from there. Deep learning is really just shape management. If your shapes don't match, your code crashes. Always check .shape. Memorize it. Here's the crucial insight. Deep learning is 90% shape management. If your shapes don't match when you do math, Python crashes with a dimension error. You will see this error hundreds of times. Always print .shape when debugging. Sometimes you have a 2x2 square, but you need a flat line of 4. .view reshapes the data without changing the contents. It's like unfolding a cardboard box. Why is this useful? Different layers in a neural network expect different shapes. After a convolutional layer, you might have a 3D tensor, but a linear layer expects a 1D tensor. View is how you convert between them. Broadcasting. This is magic. If you try to add a small tensor to a big one, PyTorch automatically stretches the small one to match. It saves you from writing loops. Without broadcasting, you'd need a for loop. With broadcasting, one line. The library does the repetition invisibly. Faster code, less bugs. Chapter 2, Autograd. This is why PyTorch beat TensorFlow. It records your history like a surveillance camera, so it can rewind time later. Neural networks work the same way. The output is wrong. We need to trace back which weights caused the error. Autograd does this automatically. We create a tensor with value 2.0. Notice requires grad equals true. This flag tells PyTorch, start recording. Every math operation on this tensor from now on will be tracked in a hidden graph. We compute y equals x squared plus 5, so 2 squared is 4 plus 5 is 9. But secretly, PyTorch is building a tree. Y connects to a square node, which connects to x, and an add node, which connects to 5. You do the math, you get a result. Then you call dot backward. PyTorch runs the tape in reverse and calculates how much each input contributed to the output. Mathematically, y equals x squared plus 5. The derivative dy dx equals 2x. At x equals 2, that's 2 times 2 equals 4. We print x.grad and confirm 4.0. PyTorch calculated calculus for us automatically. Why do we care? These gradients tell us how to nudge x to reduce y. If we want y to decrease, we move x in the opposite direction of the gradient. This is the foundation of learning. Sometimes we don't want to record. Maybe we're testing the model, not training. Recording wastes memory. Torch.no_grad is a context manager that pauses recording inside its block. Saves RAM, speeds things up. Optimizer.0_grad. Critical. Gradients accumulate by default. If you call backward 3 times, the gradients add up. Before each training step, you must reset them to 0. Chapter 3, the ritual. Every neural network, from a chatbot to a self-driving car, runs this exact same loop. Memorize it. We do this thousands of times. An epoch is one full pass through your entire dataset. It takes many epochs to learn anything complex. For batch and DataLoader, we don't feed one example at a time. We feed batches, maybe 32 or 64 examples at once. This is faster and produces smoother learning. Prediction equals model of batch. This is the forward pass. Data goes in, prediction comes out. On day 1, this prediction is random garbage. That's expected. The model hasn't learned anything yet. Step 2, the loss. You calculate how wrong the guess was. This is a single number. Big number means bad robot. Small number means good robot. Step 3, backward. Calculate the gradients. Find out which weights are to blame for the error. Step 4, the optimizer step. Nudge every weight slightly in the opposite direction of the error. We're rolling down the hill. Step 5, 0 grad. Wipe the slate clean for the next batch. Do not forget this, or your training will explode. Predict, measure error, calculate blame, update, reset, repeat a million times. That's the ritual. Every AI in existence runs this loop. Chapter 4, the architect. Building networks by hand is painful. PyTorch gives us Lego blocks inside torch.nn. The linear layer, it connects every input to every output. It's the standard workhorse of deep learning. It has weights and biases built in. What's actually happening? Each output is computed as W1 times input 1 plus W2 times input 2 plus W3 times input 3 plus bias. The layer has 3 times 5 equals 15 weights plus 5 biases. 20 learnable parameters. nn.Relu. Relu stands for rectified linear unit. It's an activation function. It does one thing. If the number is positive, keep it. If it's negative, replace it with 0. Why do we need this? Linear layers can only draw straight lines. But Relu adds nonlinearity. It's like adding bends to a straight road. This simple change lets networks learn curved, complex patterns. You can stack these blocks: linear, Relu, linear, sigmoid. This is n sequential. It packages your layers into a single pipeline. Let's trace through. We start with 2 inputs. The first linear layer transforms 2 to 8. Then Relu zeroes out negatives. The next linear transforms 8 to 8. Another Relu. Finally, the last linear transforms 8 to 1. Why do we stack them? The hidden layers allow the model to learn complex patterns. The deeper the network, the smarter the brain. Chapter 5, Classification. Let's make this real. We're going to teach a machine to separate red dots from blue dots. The raw output of a neural network is called logic. Logits. They can be any number. To turn them into probabilities, we use a softmax. Torch.softmax converts logits to probabilities. It squashes them into the range 0 to 1 and forces them to sum to exactly 1. Now we see 85% class 0, 3% class 1, 12% class 2. CrossEntropy loss, the standard loss for classification. It measures how surprised the model is by the correct answer. If the model predicts 99% cat and it's actually a dog, huge loss. One detail, CrossEntropy loss in PyTorch applies softmax internally. You pass in raw logits, not probabilities. This avoids numerical issues. To get the actual prediction, we call argmax. This returns the index of the highest value. If logits are 2.5, -1, 0.3, argmax returns 0. The model predicts class 0. Chapter 6, Data. Your model is only as good as your data. PyTorch has 2 tools to manage this: the dataset and the DataLoader. The dataset class is like a menu. It tells us how many items there are and how to get the ith item. You override len and get item. This design is clever. The data doesn't need to be in memory. Get item can load from disk, download from the internet, generate on the fly, as long as it returns the right sample when asked. DataLoader wraps the dataset and handles batching. Batch size equals 32 means every iteration gives us 32 samples at once. Shuffle equals true randomizes the order each epoch. In the training loop, we iterate over the loader. Each iteration gives us a batch of data and a batch of labels. We pass batch data to the model, get predictions, compute loss, and continue. Chapter 7, Immortality. You trained your model for days. Do not lose it when you close the script. You need to save it. Model.stateDict returns a dictionary. Keys are layer names like layer1.weight. Values are the actual tensors containing learned numbers. This is the brain of your model. Use torch.save to write this dictionary to a file. Usually with a .pt extension, it's basically pickling the brain. To bring it back, create a fresh model instance and use load.stateDict. Now your model remembers everything it learned. You can deploy it anywhere. Model.eval switches the model to evaluation mode. Some layers behave differently during training versus testing. Dropout is disabled. Batch norm uses running statistics. Always call eval before testing. Once saved, your model can be loaded anywhere. A server, a phone, a web browser. This is how AI gets deployed to production. Train once, save the weights, load them everywhere. You built a brain. Part 1 complete. Next up, computer vision and CNNs. Teaching our AI to see, recognize, and understand the world. Subscribe for Part 2.